Today I will present our work, marketing budget allocation with offline constraint deep reinforcement learning. This is a joint work with my colleagues from Ant Group. So I will start by introducing the budget allocation problem. Our research is motivated by a real-world online marketing campaign where a digital payment app, the Alipay, distribute cash coupons to improve users' engagement. In this campaign, users can use 1 cash coupon per day and a budget of 800 million yuan or send in a month. The goal is to maximize the users' engagement measured by the weekly average daily active pay users, that is the weekly DAU, which is a long-term matrix. So under a given budget limit, how to effectively allocate budgets to maximize some matrix is a typical budget allocation problem. It is widely used in industry and is very challenging. In general, allocating more budgets yields better matrix, but may exceed the budget limit. Hence, it is like a recommendation task with an additional constraint. Although we focus on marketing campaign scenario, we want to emphasize it is also commonly studied in applications like real-time bidding in online advertising or stock pacing in recommendation. We reviewed the existing method for the budget allocation problem. Conventional method takes a 2-stage procedure, but they fail to consider the long-term effect, such as the DAU matrix over a week. To optimize such long-term matrix, constrained RL approaches were proposed. The on-policy constrained RL method requires training with simulators, which are very difficult to build in industry scenarios. The offline constraint RL method learn with offline data sets only. Though they are promising, existing methods either do not converge or require an unacceptable memory cost in large-scale industry usage. We first conduct experiment to verify the significance of studying the long-term effect in budget allocation problem. To the best of our knowledge, this is the first rigorous empirical evidence confirming the necessity to study the long-term effect in budget allocation problems. So conventional 2-stage method first build a response prediction model to estimate some short-term matrix under different coupon values, such as the user DAU in the coming day. This enables calculating the matrix changes when spending more money on each user group. For example, here we have that if spending 2 more yuan, and the matrix for each inactive users will increase by 0.15. Using these predictions, the second step perform a linear optimization and get the allocation plan for each user group that maximize the short-term matrix under a budget constraint. So here are the allocated plan. However, using the real-world data from the aforementioned marketing campaign, we show the gap between the short-term and long-term matrix. In the last row here, the difference of the matrix change between these 2 groups of users vary a lot from 1 day to 7 days. It changes from the 32% to 82%. That's a large change. And this shows that use the short-term 1-day matrix will significantly underestimate the potential gain of allocating more budgets to the inactive users in the long run, the 7 days. This results in a non-optimal policy. This result rigorously verifies the importance of studying the long-term effect in the budget allocation problem. After verifying the necessity of studying the long-term effect, these 3 challenges motivate us to reformulate the budget allocation problem as an offline constraint RL problem. Specifically, we use the short-term matrix R and the short-term cost C to define the cumulative reward function GR and the cumulative cost function GC to take long-term effect into consideration. Note that although value-based methods such as Q-learning, DQN, and DDPG are widely used in offline RL, applying such method to offline constraint RL are non-trivial, because with constraints, the optimal solution may require a random play between 2 actions with a specific probability. For example, in this case, if we limit the cost, then the optimal strategy may require randomly allocating part of these blue users to 2 yuan and the others 1 yuan, where the percentage is determined by the constraint value. In this example, the optimal policy exists, but cannot be found using value-based method. Hence, the existing offline constraint RL method are divided into 2 branches. The first find a single policy that performs the best, and we call it the single best method. Though empirically performs well, they may not converge as shown in this left example. The other approach uses mixed policy, which contains multiple individual policies. By storing multiple individual policies and randomly choose one of them, this method ensures convergence. However, directly implementing such method requires memory cost, which is linear to the training step, which is unacceptably high in large-scale industrial usage. We then introduce our proposed method, which is based on the existing mixed policy method. So given the aforementioned constraint formulation, the mixed policy method first transforms it to an equivalent unconstrained equilibrium finding problem by introducing a Lagrangian multiplier, this lambda. From a game theoretical perspective, this unconstrained problem can be viewed as a two-player zero-sum game between a lambda player and a policy player, and can be solved by this mixed policy algorithm. This method iterates for t round, and each round, the Lagrangian multiplier lambda is updated by any no-regret online learning method. And then any policy that optimizes the function L under the current lambda is found. After t round, the mixed policy that uniformly play any of the found policies is returned. Due to this average operation, we call it the mean method. We show an example of how to use this meta algorithm. For example, the lambda player can be updated using the online gradient descent, OGD, with a diminishing learning rate, the eta t. And the best response player can be constructed using the Q-learning. After some math, we can show that by penalizing each reward with a lambda times c and construct a new data set, d lambda. Then we directly applying the Q-learning on this new data set yields the required best response policy under the current lambda. However, this mean method has practical difficulty to work with deep RL. In deep RL, each policy requires storing a copy of the neural network. In practice, directly applying this method requires storing hundreds copies of the neural network parameters, making it infeasible to apply in large scale. To solve this practical difficulty when working with the mixed policy, we introduce our AIN-based method. We define the measurement vector to be the vector containing the cumulative reward and cost. The active policy set of a mixed policy to be the set of individual policies with non-zero probability. Note that when using the deep RL method, the size of the active policy set determines the number of neural networks to be stored. We then define the affinity independent mixed policy, the AIM policy. A mixed policy is said to be an AIM policy if the set of measurement vectors of its active policies are affinity independent of each other. Recall that in an n+1 dimensional space, there are at most n+2 affinity independent vectors. Therefore, intuitively, AIM policy characterizes a family of mixed policy with a relatively small active policy set. So based on computational geometry, we propose a method to maintain a mixed policy and AIM policy throughout this learning process. By designing carefully updates for the set of the active policies in 3 different cases, we ensure that the target mixed policy can be expressed as a convex combination of the active policies, whose measurement vectors are affinity independent. This resulting AIM mean method, depicted in the right, achieves the same performance as the original mean method while maintaining an AIM policy. In this 2-dimensional case with a scalar constraint and a scalar reward, it is clear that any mixed policy can always be expressed as a convex combination of at most 3 individual policies. In practice, previous results show that the single best method empirically outperformed the mean method. One possible explanation is that in the mean method, every individual policy have a same 1/t weight in the final mixed policy. Intuitively, this gives bad policy the same weight as those good policies. Inspired by these findings, we propose the AIM greedy method. It maintains the AIM property same as the AIM mean method, but instead of tracking the average of all found policy, it performs a line search between the previous mixed policy's measurement vector and that of the new policy. Intuitively, this gives higher weight to the good policies and delete bad policies that were dominated by assigning their weights to 0. So our theoretical analysis shows the same convergence of the mean and aim-mean method. For the empirically better performed single best method, we show that our proposed aim greedy always dominates this method, and its performance is no worse than any single best policy. Moreover, concerning the storage problem, that is the policy efficiency, we show that both aim-based methods enjoy the optimal policy efficiency needed to ensure the convergence. So we're coming back to the question. Sorry. So we come back to this question. To spend 800 million in a month, how would you do that? Here we discuss our practice and the empirical result. We first use an online A/B testing system to collect a small percent of random samples for offline experiments. In the offline experiments, we first compare our proposed method with the classic two-stage method, the widely used DeepFM and DIN, that optimize short-term one-day DAU metric. We then compare our proposed method aim-mean and aim-greedy with the single best method. We implement them using three RL methods: the commonly used DDQN, the SOTA EDRR, and the representative offline RL method, the BCQ. Result by an average of 5 runs are obtained, and for each method, we report 3 metrics: the one-day DAU on 2 datasets. The one-day DAU measures the immediate effect of the marketing campaign, and the average DAU over 3 days and 7 days measures the long-term effect of running the marketing campaign. So from this table, we have the following observations. First, though the conventional method yields a nice result in optimizing the short-term metrics, the one-day DAU, they are outperformed by the offline constraint RL method when considering the long-term effect, the 3-day and 7 days DAU. Secondly, though makes a theoretical guarantee using a single batch Q network outperforms the aim-mean method. Meanwhile, both are consistently outperformed by the aim-greedy method, which verifies our theoretical analysis. Then this figure shows the number of stored parameters in the original mean method and the aim-based method during the training process on full dataset. It is clear that directly applying the original mixed policy approach suffers from an impractical memory cost. In contrast, our proposed method significantly reduces memory costs to at most a constant, which is favorable for large-scale industrial scenario. With this promising offline experimental result, we deploy the BCQ and aim-greedy to our large-scale online marketing campaign. The left figure illustrates the online request serving process and the offline training procedure. On the right, we show the online experimental result. After running the experiment for a week, our method improves the weekly average DAU by 0.6 for the whole app. Meanwhile, it reduces the coupon cost by 0.8%. Both are very statistically significant, increasing the millions of payment DAU while saving millions of budget. Our analysis shows that it allocates more budgets to inactive users, and hence improving the new users' engagement. The model was then successfully deployed to the full traffic. In summary, our contributions are threefold. First, we rigorously verify the long-term effect of the marketing budget allocation problem. Then, we formulate the task as an offline constrained deep RL problem and propose 2 methods to solve it while effectively reducing the number of stored individual policies to a constant. Both methods have theoretical guarantee provided. Finally, empirical results demonstrate the superior performance and policy efficiency of the proposed method, and the proposed method has been successfully deployed on a large-scale online marketing campaign with tens of millions users and more than $1 billion marketing budget. So that's it, and thank you.